Okay, so taking it aside from where we were, Avogadro's hypothesis, which a hypothesis is essentially an idea. At the same temperature and pressure, gases with the same volume consist of the same number of particles. Now this, I'm going to say, is partially true for now, but it's not, I don't want to say it's completely untrue. It will work very well for us in this class. Sorry, I got distracted. Someone walked a dog by in New Tech, so that's why I got a little paused up there. It's not completely untrue. So it works for this class, and it will work a lot of the times in real life, but it doesn't work every time. So let me show you an example of where this kind of starts to challenge some of the previous held beliefs that you might have had. So assume we have equal volumes of gaseous H2. This is H2. That doesn't look like a very good 2, but it is. Let me rewrite it. H2, okay, H2, O2, and S8 at 300 Kelvin and 1 atm. So all three of these gases are at the same temperature and pressure. Which do we have the most of? Now, it's equal based off of this, right? Equal amounts. Okay, this should not make sense to you. You should not be comfortable with that, taking my word for it. The reason that you shouldn't be comfortable with that is S8 is much bigger than O2, and it's much bigger than H2 over here. H2, sorry. So why would it take up the set, like why would these have equal number of particles if this is so much bigger, right? If they all have the same volume, we should think that bigger particles, it'll take less of them to make up that volume, right? So we should think that this is the least, this is the second least, and this is the most. But that's not the way it works. The volume of a gas is not determined by the particle size because these particles are already so small. The particle size really has a negligible effect on the volume of the gas. What determines the volume of the gas are pressure, temperature, and the amount of particles that you have. Okay, if pressure and temperature are the same, then you have equal number of moles. Okay, so these are all equal. I want to move on to the ideal gas law now, and this is an equation to quantify how much of a gas you have. So it is PV equals nRT. You can say PUVNRT to remember that. I've heard kids say pervert, whatever you want to say, okay, to remember it's PV equals nRT. This is one of the equations you do need to remember. Pressure times volume equals number of moles times some constant R times temperature, okay? So R is called the gas constant. It's got some wild units. These are the units over here, liter atm per mole Kelvin. Before you have a panic attack, it's not that crazy, right? If pressure is atm, volume is liters, this is moles, and this is Kelvin. This has units to match the other things in the equation. So we've got atm for pressure times liters equals, and let's forget about R for a second, equals moles times Kelvin. Well, obviously this is not true, right? This makes no sense. ATM liters equals moles times Kelvin is not true. So you need a constant to make this true. So the constant is liters, has units of liters times ATM per mole times Kelvin. Okay, some of you guys are going to think that I'm being a little ridiculous. This is a little cheap, I guess. This isn't fair what I'm doing. But look, moles cancel, Kelvins cancel, liter ATM on the same side. Okay, so the constant just is something that makes the math work. It's a constant of proportionality. If you really need extra clarification on that, it's the slope of the line when you plot pressure volume against number of moles times temperature. It's just the slope of the line. So we found that number to be 0.082 liter times ATM per mole Kelvin. So I'm going to introduce a concept that you'll use a lot in this class, and that is the volume of an ideal gas at standard temperature and pressure. Standard temperature and pressure are, and I have these out of order, Temperature, this is the standard temperature, 0 degrees Celsius. This is the standard pressure, 1 atm. So what's the volume of an ideal gas? And really, every gas in this class is ideal. Okay, so really just a gas. But what's the volume of an ideal gas if we have standard temperature and pressure? So PV, dang it. I hate when I accidentally click the button on the mouse and it makes it scroll while I'm writing. Okay, PV equals nRT. We want to know what the volume is. So we're solving this for volume. Volume equals nRT divided by P. Plug in your numbers. So, oh, and this should say what's the volume of 1 mole. So sorry if I've given someone a panic attack. What's the volume of 1 mole of an ideal gas? Okay, what's the volume of 1 mole of an ideal gas at standard temperature and pressure? So N equals 1 mole. We have 1 mole of the gas. R is a constant. T is 0 Celsius, but we need it in Kelvin. So now is a great time to learn the conversion from Celsius to Kelvin. 0 Celsius is equal to 273 Kelvin, 0.15 Kelvin. Okay, so any number you have in Celsius, add 273.15 to it, and you've got it in Kelvin. R, let's write our constant down, 0.082 liter ATM per mole times Kelvin, and P is 1 atm. All right, you plug these numbers in, you'll get V. So let's go ahead and do that real quick. 1 mole. R, we've got 0.082 liters times ATM per mole times Kelvin. T, we've got 273.15 Kelvin over P, which is 1 atm. So we don't have to worry about these ones, right? So it's 0.082 times 273. Let's do that math real quick. Okay, 22.4. 22.4 liters. So 1 mole of an ideal gas at standard temperature and pressure is 22.4 liters. You're going to need to know this identity throughout the rest of the course. So 1 mole of an ideal gas, 1 mole of an ideal gas equals 22.4 liters. And this is at standard temperature and pressure, at STP. Okay? Keep this in mind throughout the rest of the course. It will make some mathematical calculations for you easier.